My name is Mariano Zaron, and in this video, I'm going to talk about the main functionalities of the mocax library. So what is the main functionality of the library? It is essentially given a function that you want to approximate, is create a replica of it, which is given by an object that we call the mocax object. And the second part of it is that we want to be able to evaluate that object. So let's take a look at the problem that we have. So consider a function that you want to approximate. And just to keep it simple, let's assume that the dimensionality of the function is 1. The first thing that we need to specify is the domain of approximation. The domain of approximation is determined by an interval that we denote here by a comma b. The second part that we need to define, or the second thing that we need to specify, are the Chebyshev points within that interval. So I'm going to denote those Chebyshev points by these crosses here. And the third part that we need are the values of the function f on these points. And I'm going to denote with these round balls here. So that is all that we need in order to be able to come up with a Chebyshev object. So I've prepared some example code here to show you how this is scripted. So first of all, let's choose the function we're interested in approximating. This is in our case the Black-Scholes function that I'm highlighting here. Then first thing is we need to specify the number of dimensions that we're interested in. This is done by passing an integer to the initializer of the mocax class. The integer is this one up here that you see that I've called num dimensions. Now, the domain that we need to define, that we have over here between a and b, is just an interval, is specified down here. So all the information that we need of the domain of approximation is captured in this variable called domain. The other bit that we need to specify is the Chebyshev points, which are denoted by these asterisks. The Chebyshev points, the information of the Chebyshev points is contained in this object here, which is defined by this variable called ns. And once you've got these parameters, we can pass them to the initializer of the object that I've highlighted here to come up with an object that can be evaluated. I'll give you more details. I'll go into more details of the construction of the object, but for the time being, what I wanted to see is that these very few parameters control pretty much everything that we want the object to be able to do. So let's take a look at what happens when we build the object, evaluate it on a collection of points, and we compare those values to the real values that you have from the function you want to approximate. Again, the function we want to approximate is the Black-Scholes function, which I've got over here. If I run the script, taking as the interval where I want to approximate the Black-Scholes function to be between 30 and 150, and let's take a Chebyshev size of 3. So you're only choosing a couple of Chebyshev points or a few Chebyshev points. What happens if we run it? We obtain, as you can see on the right-hand side, you've got two plots. The one on the left-hand side contains both the values of the Chebyshev object and the values of the original function that you can see are not the same. The blue one is the one that corresponds to the Chebyshev object, or the mocax object, sorry. The other one is the actual function. And you see down here, I've printed the maximum error is an error of 3. What happens if you start tweaking the parameters, in particular, the one that controls the size of the Chebyshev mesh, which is the one that controls the accuracy of the approximation? If you increase that to only 5, you'll see already a big difference. You can still see both functions here, but they're barely indistinguishable just by looking at them. And the maximum error is already of 6 times 10 to the minus 1. If you increase that to 10, now you can't distinguish the functions, and the error is of the order of 10 to the minus 3. Go to 15, and that error gets reduced even further to 10 to the minus 4, and so on. If we went all the way to 25, for example, we would get much more accuracy, 10 to the minus 8, which is way more than you would need. So essentially, this is the way that you control the accuracy of your function. Of course, You can change the domain of approximation. If you're not interested in approximating the function between 30 and 150, but let's say between 40 and 150, you just change it there, run it again, you've built the object, you've evaluated it, and you've compared it to the original function that you wanted to approximate. Good. Now, let's go back to the script where I showed you how to specify the parameters to build a function, and I'm going to give you a bit more detail about each of them. So it's convenient to have the documentation ready available, the mocax documentation. I'm just going to go to the main page of the documentation. The library is object-oriented, so everything revolves around classes. Let's go to the list of classes. These are all the classes. The main class, which is the one that defines the mocax object, or the one that instantiates the mocax object, it's called mocax. Let's take a look at its initializer. So you've got the initializer here, all the associated methods. We go to the initializer, we see all these parameters that need to be specified. So let's go back to the code and we'll describe them. So the first one is just the number of dimensions. Very easy to specify. It's just an integer. Let's go now to domain. Domain gives you, it's essentially a list of intervals. In this case, we only have one dimension. So domain values, which is a list of intervals, is a list of one single interval. The interval here in our graph would be just simply a comma b. If you had a function which has more than one dimension, you would have more intervals that you need to include in this list. And then you pass that list to the initializer of a class that we call mocax domain. So the domain that needs to be passed to the initializer of the mocax class is in itself a class that we've defined within the library. If it was only a one-dimensional case that we were interested in, it would be easy to just pass an interval as a parameter to the mocax initializer, and that will be it. But given that we're interested also in building objects of higher dimensions, that becomes a bit more complicated, and it becomes a bit more difficult to follow. The scripting becomes a bit more dirty. So we've created classes for quite a few of the parameters that you need to pass to the mocax initializer, and it's the case for the domain. So you pass this list of intervals to the initializer of mocax domain, and you get an object of type mocax domain that we've called domain, and which can be passed here, as you see, to the initializer of the mocax class. So that takes care of the interval or the domain where you want to approximate the function. Now, what about the mesh of Chebyshev points? How do you control, how do you tell the initializer that you want X number of Chebyshev points? That is controlled by another class within the library called mocax_ns. And in order to instantiate an object of type mocax_ns, you need to pass a list of integers, of positive integers. In this case, we only have one dimension, so you only specify one integer, which in this example is 10. You pass it to the initializer and you get an object, in this case that we've denoted by ns. But then you can pass to the initializer of the mocax class. So far, we've been able to specify domain of approximation, the Chebyshev points, and there's one thing missing in order to be able to use a mocax object, and that is the value of the function on the Chebyshev points, which is very important as well. So there are two ways of telling the mocax object what the values of the function is, what the values are on the Chebyshev points. One of them is by simply passing the function as a parameter to the initializer. That will be passed as a first parameter. Now, sometimes that can be complicated. First of all, the function needs to be written in a particular way. So it may be complicated to change the function that somebody gave you so that you can pass it as a parameter to the initializer. But another one could be that the function you're interested in is in some other system. It could be a front office pricer to which you barely have any access. The only thing that you can do is send values where you want it to be evaluated. Someone else will evaluate them and they'll return the values, but that's it. So for those kind of instances, we've allowed the construction of the object to be done in two stages. The first one is where you pass only the domain and the size of the Chebyshev mesh. Instead of passing the function as a first parameter, you pass a non-value, and that is it. The object that returns, that we've called here mocax object, is an object that is only able to tell you where the Chebyshev points are. So if we run this bit of code so far, what we obtain is an unfinished construction of an object that then can tell you where it needs the values of the function to be. So how do we get these points? So these points are obtained by calling the method getEvalPoints of the Chebyshev object, of the Mocax object. That returns this variable called anchor points. So we run that. You'll see that anchor points here is a list of values. And that list of values is the one that you then need to pass to the function. So you may need to save that into a file, send it somewhere else. Someone else will load it, evaluate the function you're interested in on those points, and then they'll send them back. And you'll have to load them up again to finally feed them into the object, to finish the construction so that you can use the object to be evaluated. So this is what we do in this bit of code, where you call the method setOriginalFunctionValues. You pass to that function the values at the anchor points, and that finishes the construction. So once we've run this bit of code, what you end up with is a Mocax object that is not unfinished, so it doesn't raise this warning that you saw before, or this message, doesn't send this message that you saw before. And here you've got the characteristics of the object that you've built. So that's all you need in order to build the object. In a separate video, we'll cover how to build the object if you have access to the function, you modify it appropriately so that you can pass it as a parameter here instead of the non-value that we used. But for the time being, we're going to stick to this very simple way of building the Mocax object. I personally prefer this way because it gives me more control over every step of the process. So let's go now and see how to evaluate this object. Let's go back to the documentation. At the top of the documentation of the Mocax class, you'll see this method, eval. If we click into it, we see that eval takes two parameters, point and derivative ID. Derivative ID is something that we won't go into for the time being. That's going to be covered in a separate video. Comes with a default value of 0, which basically means I'm only interested in replicating the original function and no derivative of it. But what's important is that you need to pass a point. The point needs to be a list. So what we do is, let's say that you're interested in evaluating the object at collection of points in the domain where you've created the Mocax objects, which is usually the case when you want to run risk calculation. These are the points you're going to be interested in evaluating. Those points are the ones that I've defined here by the variable points. And by defining or by writing a for loop, I can go point by point and feed them into the eval method. It's important to notice that the eval method only takes one point at a time. It's not going to be able to take the whole collection of points. But you do that simply by writing this for loop, which is very straightforward. Gave me an error because I hadn't run the building part, but now I do it. I've built my object and I've evaluated it. One thing that I haven't mentioned, which you've probably already noticed, is that I've enclosed pretty much all the bits and pieces that I write using methods and initializers from the library. I've included them within a try clause. The reason is that if the library has some exceptions inbuilt into it. So it raises exceptions when parameters that you shouldn't be passing are passed. So as a simple example, let's say that here, for the parameter of n equals 10, I pass minus 10 instead of 10, which wouldn't make sense because 10 refers to the number of Chebyshev points that I've got here. I can't pass something less than 1. If I do that, then immediately the library will raise an exception that if you catch and deal with it appropriately, that allows you to keep your code running properly and so on. Otherwise, you'll just stop, raise the error, but it will raise something, it will raise an exception like this, error mocax exception. The accuracy parameters cannot be less than 1. So if you go to the documentation, you'll see everything there is about the class that implements mocax exception. So we've already seen how to build the object, how to evaluate it, and that's essentially it. That's the main functionality that the library provides. And we go back again to what we saw at the beginning. We can wrap everything that I did into a few lines so that you can build the object over here by passing the appropriate parameters. You can then evaluate the object that you've created. And then finally, if you want, you can compare it to the original function. And that is it. And you get really good degree of accuracy even with a small value event. So what we've seen in this video is the main functionality of the library, which consists of creating a mocax object that replicates a function that then you can evaluate. In future videos, we'll show you some of the other functionalities that the library provides, such as being able to replicate the derivatives, being able to create splines of Chebyshev, and much more. Thank you very much.